Alright, let's go. Number 10. The Kaluza-Klein dimension. In 1919, Theodor Kaluza, a mathematician at the University of Königsberg in what was then Germany, mailed a paper to Albert Einstein proposing that the universe contained a fifth dimension, a spatial dimension, beyond the three of ordinary experience. Curled into a circle so small it was undetectable by any instrument then in existence, and that the existence of this dimension, when written into the field equations of general relativity, produced Maxwell's equations of electromagnetism as an automatic consequence. Einstein held the paper for 2 years before recommending it for publication in the Proceedings of the Prussian Academy of Sciences in 1921. In 1926, the Swedish physicist Oskar Klein independently refined the proposal, calculating that the compactified dimension would need to be curled at the Planck scale approximately 10 to the power of -35 meters, or roughly 100 million billion times smaller than a proton to have escaped detection. The combined framework became known as Kaluza-Klein theory and has remained a foundational reference point in theoretical physics for more than a century. The claim Kaluza made was not that an extra dimension might exist as a speculative possibility. It was that the unification of gravity and electromagnetism, the two forces known to physics in 1919, required it. The mathematics did not accommodate a fifth dimension. It demanded one. When the field equations of general relativity were extended to 5 dimensions and the fifth dimension was compactified, electromagnetism did not need to be inserted into the theory. It fell out of it. The unification was exact, automatic, and deeply strange. Two apparently unrelated forces turned out to be the same force viewed from different dimensional perspectives. The credibility of the framework was substantially extended by string theory, which beginning in the 1980s required not one additional dimension but 6 or 7, compactified at or near the Planck scale, to produce a mathematically consistent theory of quantum gravity. The superstring revolution, documented across foundational papers by Michael Green and John Schwartz in Nuclear Physics B in 1984, and subsequently developed by Edward Witten at the Institute for Advanced Study in Princeton, whose contributions to string theory earned him a Fields Medal in 1990. The only physicist to receive mathematics' highest honor, produced a framework in which extra dimensions were not an option, but a requirement for internal consistency. The Large Hadron Collider at CERN, the 27-kilometer ring beneath the French-Swiss border that is operated at collision energies up to 13 teri-electron-volts, was designed in part to search for signatures of Kaluza-Klein excitations, heavier copies of standard model particles that extra-dimensional theories predict should appear at high enough energies. No such excitations have been detected as of the time of writing. What makes this genuinely creepy, rather than merely a technical question about the geometry of spacetime, is the spatial relationship the theory implies. A compactified extra dimension is not somewhere else. It is here, threading through every point in the three-dimensional space of this room, curled at a scale too small to resolve. Present in every cubic meter of apparently empty space, at a density that makes the concept of emptiness provisional. The extra dimension is not a place you could travel to. It is a direction you cannot point in, running through the interior of every object and every gap between objects simultaneously. The mainstream response to Kaluza-Klein theory is precisely calibrated. The theoretical framework is taken seriously. It is embedded in the foundation of string theory, which is the dominant approach to quantum gravity among working theoretical physicists. The specific claim that extra dimensions are detectable at LHC energies has been falsified in the sense that the predicted signatures have not appeared at the energies so far explored, which constrains, but does not eliminate the parameter space. The consensus position, represented in review papers by Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali, whose large extra dimensions proposal, published in Physics Letters B in 1998, suggested extra dimensions might be as large as a millimeter rather than Planck scale, is that the absence of a detection narrows the theory's viable parameter space without closing it. The dimensions may simply be smaller or larger than current experiments probe. What the mainstream position does not address is the implication Kaluza himself drew in his 1919 paper, in a passage Einstein found compelling enough to quote in his covering letter to the journal. Kaluza noted that the fifth dimension's invisibility was not a defect of the theory, but a feature of the geometry, that a being confined to 3 spatial dimensions would have no sensory access to a fourth or fifth, regardless of how present those dimensions were. The invisibility was structural. It was not a matter of resolution, it was a matter of confinement. A dimension that contains us, that threads through us, that we cannot point to or measure directly, and whose existence the mathematics of our best physical theories requires, is not an absence. It is a presence we have no instrument to confirm. Number 9. The brain collision hypothesis. In 1999, Lisa Randall, a theoretical physicist at Harvard University, and Raymond Sundrum, then at Boston University, published 2 papers in Physical Review Letters Volume 83, Issues 17 and 23, that proposed a model of extra-dimensional geometry in which our entire observable universe exists as a 3-dimensional membrane, or brain, embedded in a higher dimensional bulk space they designated the warped geometry model. The papers, which have accumulated more than 10,000 citations each in the subsequent literature and are among the most referenced theoretical physics papers of the past 3 decades, proposed that the bulk space contains at least one additional brain parallel to ours, separated from our membrane by a gap in the extra dimension that is small in the higher dimensional geometry while being effectively infinite from the perspective of any observer confined to either brain. The Randall-Sundrum model was not proposed as a speculation about parallel universes. It was proposed as a solution to the hierarchy problem, the unresolved question of why gravity is approximately 10 to the power of 30, 6 times weaker than the electromagnetic force. A disparity so extreme that no mechanism within standard 3-dimensional physics had successfully accounted for it. The solution the model offered was geometric. Gravity, unlike the other fundamental forces, is not confined to our brain. It propagates through the bulk. The weakness of gravity as experienced in our universe is a consequence of its dilution across the extra-dimensional volume. Separating our brain from the bulk, the gravitational field spreads into dimensions we cannot access. And what we measure as gravity's strength is the attenuated residue that reaches us after propagating through a space we have no direct knowledge of. The other forces, electromagnetism, the strong and weak nuclear forces, are confined to our brain by the physics of the model, which is why they retain their full strength while gravity appears, from our dimensional perspective, absurdly weak. The hierarchy problem is not a fine-tuning accident. It is a geometric consequence of our brain's position in a higher dimensional space. The experimental signature of the Randall-Sundrum model is the graviton's Kaluza-Klein tower, a series of massive graviton excitations that should appear at the Large Hadron Collider if the model's parameters fall within a certain range. Searches for these excitations, reported by the ATLAS and CMS collaborations in papers published in the Journal of High Energy Physics between 2010 and 2023, have not detected them at energies up to 13 teri-electronvolts, constraining the model's parameter space but not eliminating it. The Randall-Sundrum framework is taught in graduate theoretical physics programs at MIT, Princeton, and Cambridge. It appears in the standard reference text on extra dimensions, warped passages, which Randall published with Alan Lane in 2005 for a general audience while maintaining her position at Harvard. What makes this genuinely creepy, rather than merely an elegant solution to a technical problem in particle physics, is the consequence the model carries for the concept of adjacency. The second brain in the Randall-Sundrum model is not in another galaxy. It is not at the edge of the observable universe. It is separated from our brain by a gap in a dimension we cannot access, and that gap, measured in the higher dimensional geometry, may be extraordinarily small, smaller than any distance we have the capacity to measure in 3-dimensional space, while remaining, from our perspective, absolutely and structurally inaccessible. The adjacent brain is, in the most precise geometric sense, right here. The gap between our universe and whatever exists on the neighboring membrane is not a distance. It is a direction we cannot move in. The mainstream response to the brain collision scenario, the specific proposal, developed by Paul Steinhardt at Princeton University and Neil Turok at the Perimeter Institute in their ekpyrotic universe model, published in Physical Review D in 2002, that our universe originated in a collision between two such branes is that the model produces a cosmological scenario that is mathematically consistent and generates predictions about the spectrum of primordial gravitational waves that differ measurably from inflationary predictions. The Laser Interferometer Space Antenna, the ESA gravitational wave detector scheduled for launch in the 2030s, may be able to distinguish between the two scenarios. The brane collision hypothesis is not fringe cosmology. It is a competing mainstream proposal with a defined experimental test. What that experimental test does not address is the prior question. If the ekpyrotic model is correct, the object that struck our brane and produced our universe is still there. The collision produced the Big Bang. The colliding brane did not cease to exist upon impact. It rebounded, or it remains in proximity, or it has drifted back to some position in the bulk, and whatever it is separated from everything we have ever observed or measured by a gap we have no means of crossing, in a direction we cannot point to, at a distance that may be effectively zero in the higher dimensional geometry. The universe may have been struck into existence by something we cannot see. That something did not go away. Number 8. The holographic bound. In 1993, Gerard 't Hooft, a theoretical physicist at Utrecht University in the Netherlands, and a recipient of the Nobel Prize in Physics in 1999, published a paper proposing that the maximum amount of information that can be contained within any region of space is not proportional to the volume of that region, but to its surface area, that a three-dimensional volume of space does not have three-dimensional information capacity, but two-dimensional information capacity, measured in units of 1 bit per Planck area, where a Planck area is approximately 10 to the power of -70 square meters. The proposal was independently developed and extended by Leonard Susskind, a theoretical physicist at Stanford University. In a paper published in the Journal of Mathematical Physics in 1995, and the combined framework became known as the holographic principle. It was given its most precise formulation by Juan Maldacena, then at Harvard University, in a 1997 paper in the International Journal of Theoretical Physics that has since accumulated more than 20,000 citations, making it one of the most referenced papers in the history of theoretical physics, demonstrating through string theory that a quantum gravity theory in a three-dimensional space is exactly equivalent to a quantum field theory on the two-dimensional boundary of that space, with no gravity at all. The claim the holographic principle makes is not metaphorical. It is not that the universe resembles a hologram in some loose analogical sense. It is that the information content of any volume of space, every particle, every field configuration, every quantum state within that volume, is fully encoded on the boundary surface surrounding it, at a density of 1 bit per Planck area, and that the three-dimensional interior is in a precise mathematical sense redundant. The physics inside the volume and the physics on the boundary are not two descriptions of the same thing. They are the same thing, expressed in different variables. This equivalence, known as the AD-S/CFT correspondence, has been tested against thousands of calculations across 2 decades of theoretical work and has never produced a contradiction. It is the most precisely verified duality in theoretical physics. The Bekenstein-Hawking entropy formula, derived independently by Jacob Bekenstein at the Hebrew University of Jerusalem in 1972, and Stephen Hawking at the University of Cambridge in 1974, had already established that the entropy of a black hole, a measure of its information content, scales with the area of its event horizon rather than its volume. The holographic principle generalizes this result from black holes to all of space. The boundary is not a special surface at the edge of something unusual. It is a property of space itself. Every region has a boundary. Every boundary encodes everything inside it. The interior is a projection. What makes this genuinely creepy, rather than merely a profound result in quantum gravity, is the spatial inversion it performs on the concept of inside and outside. If the holographic principle is correct in its general form, and Maldacena's correspondence has given it the strongest mathematical foundation of any framework in modern theoretical physics, then the three-dimensional space in which all experience occurs is not the fundamental layer of reality. The fundamental layer is the two-dimensional boundary. The interior, including every object and observer within it, is encoded information read off a surface. The surface is the reality. The volume is the readout. The mainstream position, stated carefully by physicists including Raphael Bousso at the University of California, Berkeley, whose covariant entropy bound extended the holographic principle to general spacetimes in a paper published in the Journal of High Energy Physics in 1999, is that the holographic principle does not imply that the three-dimensional world is illusory in any philosophically loaded sense, that both descriptions, the boundary and the bulk, are equally valid, and that the equivalence is a mathematical tool rather than an ontological claim about which layer is more real. Bousso has argued explicitly that the holographic principle should be understood as a statement about information redundancy, not about the unreality of ordinary experience. This is the careful, defensible position, and it is held by the majority of physicists who work with the framework. What that position does not address is the directionality the framework implies. A hologram has a surface and an interior. Information flows from the surface into the apparent volume. An observer inside the holographic volume has no direct access to the surface that encodes them. The surface, in the cosmological case, is the boundary of the observable universe, the two-dimensional shell, at the edge of everything we can see or measure, approximately 46 billion light-years away in every direction, on which, if the holographic principle holds in its general form, every particle and field and configuration and history within the volume is written. The surface encodes the interior. The interior cannot read the surface. Whatever is on the other side of the surface, whatever exists outside the boundary of the observable universe, in a position to access the two-dimensional encoding of everything inside it, is not described by any physics that applies within the volume. The universe may be written on a surface that faces outward. We are on the inside. We have no way to read our own encoding, and no way to determine whether the surface faces anything at all. Number 7. The dark matter shadow. In 1933, Fritz Zwicky, a Swiss astronomer at the California Institute of Technology in Pasadena, measured the velocity dispersion of galaxies in the Coma Cluster, a gravitationally bound collection of more than 1,000 galaxies, approximately 320 million light-years from Earth, and found that the galaxies were moving far too fast to be held together by the gravitational pull of their visible mass. The cluster should have flown apart long ago. The visible matter, stars, gas, dust, everything detectable by any instrument Zwicky had access to, was insufficient by a factor of approximately 400 to account for the observed velocities. Zwicky proposed that the cluster contained a large quantity of material he called dunkel materie, dark matter. The result was noted, questioned, and largely set aside for 4 decades until Vera Rubin, an astronomer at the Carnegie Institution of Washington, and Kent Ford, working with a spectrograph Ford had built capable of measuring stellar velocities at the edges of spiral galaxies, published a systematic survey in the Astrophysical Journal in 1980, demonstrating that the rotation curves of spiral galaxies were flat, that stars at the outer edges of galaxies moved at the same velocity as stars near the center, rather than slowing as Newtonian mechanics predicted they should if the visible mass were all the mass there was. The finding was not anomalous in 1 or 2 cases. It held across every galaxy in the survey. The evidence for dark matter has since accumulated across independent lines of observation to a degree that places it beyond serious dispute as a phenomenon. Gravitational lensing surveys, including the bullet cluster observation published in the Astrophysical Journal in 2006 by Douglas Clough and collaborators at the University of Arizona, demonstrated dark matter's gravitational effects spatially separated from ordinary matter during a galaxy cluster collision, ruling out the most prominent class of alternative gravity theories as a complete explanation. The Planck satellite's mapping of the cosmic microwave background, published by the European Space Agency in 2013 and refined in subsequent data releases, established that dark matter constitutes approximately 27% of the total energy content of the universe, 5 times the contribution of all ordinary matter combined. The composition of the universe, on the best available measurement, is 27% something that has never been directly detected. The candidate particles propose to account for dark matter weakly interacting massive particles, or WIMPs, axions, sterile neutrinos, primordial black holes, have been searched for across decades of increasingly sensitive experiments. The Xenon 1T experiment at the Gran Sasso National Laboratory in Italy, operating a liquid xenon detector containing 3.2 tons of active material shielded beneath 1,400 meters of rock, completed its run in 2018 without detecting a WIMP interaction. Its successor, Xenon T, operating with an 8-ton active volume, has reported no confirmed detection. The LUX Zeppelin detector at the Sanford Underground Research Facility in South Dakota, the most sensitive dark matter direct detection experiment currently operating, published its first results in 2022, covering an exposure of 5.5 ton-years of liquid xenon with no confirmed signal. The parameter space in which WIMPs can hide has been reduced by several orders of magnitude across 30 years of null results. What makes this genuinely creepy, rather than merely an unsolved problem in particle astrophysics, is the framework that has emerged from the failed detection program. The null results do not rule out dark matter. They rule out dark matter that interacts with ordinary matter through the weak nuclear force at the expected cross-sections. What they are increasingly consistent with is a darker possibility that dark matter does not interact with ordinary matter through any force except gravity. Not because it is weakly coupled, but because it inhabits a parallel sector of physics entirely. A shadow world with its own forces, its own particles, its own chemistry, interacting with our sector only gravitationally, threading through every galaxy and every solar system and every room, present in quantities 5 times greater than everything we can see or touch, and detectable by no instrument we have built or could build that operates through any force other than the one that leaks between dimensional sectors. The mainstream response is that the parallel dark sector hypothesis, while consistent with all existing data, is not favored over simpler candidates on grounds of theoretical parsimony, and that next-generation experiments, including the proposed Darwin Observatory, a 50-ton liquid xenon detector, and the Axion dark matter experiment at the University of Washington, which searches for axion photon conversion in a strong magnetic field, may yet detect a signal. Catherine Zurich at the Lawrence Berkeley National Laboratory, one of the leading theorists of dark sector physics, has argued that the null results to date constrain the parameter space rather than closing it, and that light dark matter candidates below the WIMP mass range remain largely unexplored experimentally. What the next generation of experiments cannot test is the parallel sector scenario in its strongest form. A dark sector that couples to our sector only gravitationally produces no signal in any electromagnetic detector, no signal in any neutrino detector, no signal in any experiment that relies on any force other than gravity to register a particle's passage. It would be present everywhere. It would move through the detector without leaving a trace. Not because it was not there, but because the detector, and the physicist reading it, and the laboratory around them, speak a physical language that the dark sector does not share. 5 times as much of the universe is made of something we have never touched as is made of everything we have ever known. The extra items in the inventory of the cosmos outweigh us by a factor of 5. They are in this room right now, and we have 30 years of increasingly precise null results to show for our attempts to find them. Number 6. The simulation boundary. In 2003, Nick Bostrom, a philosopher at the University of Oxford and director of the Future of Humanity Institute, published a paper in the Philosophical Quarterly, Volume 53, Issue 211, presenting what he designated the simulation argument, a trilemma structured as a logical proof rather than a speculation, demonstrating that at least one of 3 propositions must be true: that virtually all civilizations at our level of technological development go extinct before reaching the computational capacity to run detailed simulations of their own history, that virtually all technologically mature civilizations choose not to run such simulations, or that we are almost certainly living inside a simulation running on the computational substrate of a civilization that has already achieved that capacity. The paper was not received as philosophy of mind speculation. It was received as a formal argument, and it has been engaged with as such by physicists including Stephen Hawking, who addressed it in his final book, and by cosmologists at institutions including the Massachusetts Institute of Technology and the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, where its implications for the physics of our universe have been examined in peer-reviewed literature. The argument's structure is tighter than its popular reception suggests. Bostrom did not claim that we are in a simulation. He demonstrated that the conjunction of two assumptions most people hold simultaneously, that civilizations do not universally go extinct before reaching mature computational capacity, and that mature civilizations are not universally uninterested in running ancestor simulations, logically entails that simulated minds vastly outnumber non-simulated ones, and therefore that any given mind, including the one reading this, is far more likely to be simulated than not. The argument does not require any physics beyond what we already accept. It requires only the assumption that computation can instantiate experience, which is the working assumption of virtually every neuroscientist and cognitive scientist alive. The physical predictions of the simulation hypothesis have been examined seriously. In 2012, Silas Bean, Zoré Davuti, and Martin Savage at the University of Washington published a paper in the European Physical Journal A. Volume 50. Proposing that a universe running on a discrete computational lattice, the most natural architecture for a simulation, would produce detectable anisotropies in the spectrum of ultra-high-energy cosmic rays, particles arriving from outside the galaxy, with energies exceeding 10 to the power of 20 electron volts. Because the lattice structure would impose a directional bias on the maximum energy propagating through it. The Pierre Auger Observatory in Argentina, which has been cataloging ultra-high-energy cosmic rays since 2004 across a detector array covering 3,000 square kilometers of the Pampas, has detected an anisotropy in the arrival directions of the highest energy events. Published in Science in 2017, the anisotropy is not consistent with the lattice prediction in its specific form, but it has not been fully explained by astrophysical source distributions either. What makes this genuinely creepy rather than merely a philosophical thought experiment is the boundary condition it places on every item this sequence has established so far. The Kaluza-Klein extra dimensions are real in the simulation only if the simulator chose to include them. The adjacent brain in the Randall-Sundrum model is a feature of the simulated geometry, not of the substrate running it. The holographic boundary encodes the interior of the simulation onto a two-dimensional surface, and that surface is not the edge of the simulator's reality. It is a feature of the simulated physics. The dark matter that threads every galaxy and every room may be a sector of the simulation's particle content that the simulators did not bother to make detectable by the simulated observers. Every anomaly in the preceding items resolves into a design choice. The strongest mainstream objection to the simulation hypothesis as a physical claim rather than a philosophical one comes from physicists including David Deutsch at the University of Oxford, whose work on the constructor theory of information argues that the computational resources required to simulate a universe at the quantum level, not approximating quantum mechanics, but running it exactly are equivalent to the resources of a physical universe of the same size, making the simulation hypothesis either trivially true in a sense that carries no information or physically impossible in the sense that would make it interesting. Zoré Davuti, in subsequent work at the University of Maryland, has argued that any detectable signature of discretization would likely have been found in existing high-energy physics data if it existed at the scales accessible to current experiments. The hypothesis survives these objections only if the simulation runs at resolutions and architectures that leave no detectable signature in the physics it simulates, which is precisely the version that cannot be ruled out. A simulation designed to be indistinguishable from base reality is indistinguishable from base reality. The Planck scale 10 to the power of -35 meters, the smallest length that has physical meaning in quantum gravity, may be the resolution limit of the computational substrate rather than a fundamental feature of nature. Every experiment ever performed has operated at scales far above the Planck length. The lattice, if it exists, is below everything we have ever measured. The boundary between the simulation and whatever runs it is not somewhere in space. It is at a scale of resolution we have never reached, in a substrate we have no instrument to probe, operated by an entity whose existence would be, from inside the simulation, formally indistinguishable from the absence of any entity at all. Number 4. The fine-tuning observers. In 1979, Bernard Carr, a cosmologist at Queen Mary University of London, and Martin Rees, then Plumian Professor of Astronomy at the University of Cambridge and subsequently Astronomer Royal, published a paper in Nature, Volume 278, titled The Anthropic Principle and the Structure of the Physical World, which systematically catalogued the degree to which the fundamental constants of physics, the strength of gravity, the mass of the electron, the cosmological constant, the strong nuclear force coupling, appeared to be calibrated within extraordinarily narrow ranges compatible with the existence of complex structures, and specifically with the existence of observers. The paper was not the first to notice individual instances of apparent fine-tuning. Brandon Carter, a theoretical physicist at Cambridge, had coined the term anthropic principle in a 1974 paper presented at a symposium honoring Copernicus's 500th birthday, published in the International Astronomical Union Symposium Proceedings, noting that what we observe must be compatible with our existence as observers, and that this constraint was non-trivially informative about the values constants could take. Carr and Rees assembled the individual instances into a systematic program and demonstrated that the coincidences were not isolated curiosities, but a pervasive structural feature of the constants that governed all of physics. The numbers are specific and verifiable. The cosmological constant, the energy density of empty space, which drives the accelerating expansion of the universe, is observed to have a value of approximately 10 to the power of negative 120 in natural Planck units, a number so close to zero relative to the values quantum field theory predicts for vacuum energy contributions that Steven Weinberg, a theoretical physicist at the University of Texas at Austin and Nobel laureate in physics in 1979, described it in a paper in Reviews of Modern Physics in 1989 as the worst failure of dimensional analysis in the history of physics. If the cosmological constant were larger by a factor of roughly 10 to the power of 50, the universe would have expanded too rapidly for gravity to assemble any structure: no galaxies, no stars, no planets, no chemistry. If the strong nuclear force were stronger by approximately 2%, that protons would be stable, and hydrogen would be consumed entirely in the early universe, leaving no fuel for long-lived stars. If it were weaker by 5%, deuterium would be unstable, the nucleosynthesis chain that produces heavier elements would not proceed, and the universe would contain nothing heavier than hydrogen. The ranges within which these constants permit complexity are not wide. They are, in several cases, parts per million of the available parameter space. The theoretical framework that most physicists currently deploy to explain fine-tuning without invoking selection by an external agent is the landscape, a term introduced by Leonard Susskind of Stanford University in a paper in the Journal of High Energy Physics in 2003, building on the string theory vacuum degeneracy identified by Raphael Bousso and Joseph Polchinski in the same journal in 2000, which demonstrated that string theory does not predict a unique set of physical constants, but permits an astronomically large number of distinct vacuum states. Estimates range from 10 to the power of 500 to 10 to the power of 1,000 each, with different values of the fundamental constants, and that the inflationary multiverse mechanism naturally populates all of these vacua, producing a vast ensemble of universes with different constants, from which observers can only find themselves in regions compatible with their existence. What makes this genuinely creepy, rather than merely a productive theoretical framework, is what the landscape solution requires when examined alongside the holographic and simulation frameworks established in the prior items. The landscape explanation for fine-tuning is an observer selection argument. It works by noting that the set of observers who can ask the question is restricted to the subset of universes where the constants permit observers to exist. The argument is logically valid. It is also, in a precise sense, an argument that says the constants appear selected for observers, because they are, in fact, selected by observers, not chosen by an agent, but filtered through the existence condition of the beings who measure them. The selection and the observer are the same event. The mainstream response, developed by physicists including Don Page at the University of Alberta, whose work on observer selection in cosmology has appeared in Physical Review D across multiple papers since the 1980s. And by David Deutsch, who has argued that the landscape multiverse is the only scientifically respectable explanation for fine-tuning that does not invoke external design, is that the anthropic landscape is a statistical explanation of the same type as any other selection effect in science, that we do not find it mysterious that we evolved on a planet with liquid water rather than on a gas giant. And fine-tuning is the same argument at cosmological scale. The landscape is preferred over the design hypothesis on grounds of parsimony, because it requires only the extension of known physics rather than the introduction of an uncharacterized external agent. What the landscape does not explain is why this universe, among the 10 to the power of 500 vacua in the ensemble, has the specific constants it has, rather than any other set compatible with observers. The anthropic filter explains why the constants are in the observer-compatible range. It does not explain which point in that range we occupy, or why. The cosmological constant is not merely small enough to permit structure. It is almost exactly the smallest value compatible with the formation of the galaxies that contain the stars that produce the heavy elements that constitute observers, a coincidence Weinberg himself noted in 1987, before the cosmological constant's value was measured, as a prediction of the anthropic argument. He was correct. The constant sits at the edge of the habitable range with a precision that the landscape, taken alone, does not account for. The constants of physics are not merely compatible with observers. They appear, in several cases, to be optimized for them, tuned not merely to permit complexity, but to maximize it. The landscape explains why the universe is habitable. It does not explain why it is, in Weinberg's words, the most habitable version of habitable that the available parameter space contains. Something set the dial. The landscape says the dial was set by the filter. The filter is us. The creepiest version of that sentence is not the one where the filter is external. It is the one where it is not. Number 3. The Boltzmann Watcher. In 1895, Ludwig Boltzmann, a theoretical physicist at the University of Graz in Austria, whose statistical mechanics had provided the first rigorous microscopic foundation for thermodynamics, proposed a solution to a problem his own work had created. The second law of thermodynamics, the principle that entropy, the measure of disorder in a closed system, increases over time, implied that the current low entropy state of the observable universe, its ordered galaxies, its burning stars, its precisely structured chemistry, was vanishingly improbable given enough time. Boltzmann's statistical mechanics described entropy increase as a consequence of probability. High entropy states are simply more numerous than low entropy states, and systems evolve toward them because there are more ways to be disordered than ordered. The problem his framework generated was that if the universe were eternal and in equilibrium, the low entropy state we observe should be extraordinarily rare, so rare that it was more probable for any given observer to have arisen as a spontaneous thermal fluctuation from an otherwise featureless high entropy background than for the entire observable universe to have fluctuated into its current ordered state. Boltzmann proposed, in a paper in the Annalen der Physik in 1895, that the observable universe was precisely such a fluctuation, a local, temporary region of anomalously low entropy embedded in an eternal, maximally disordered cosmos. The logical consequence of Boltzmann's proposal, identified by the physicist Richard Feynman in his Lectures on Physics published by Addison Wesley in 1964, and developed with precision by the cosmologist Sean Carroll, then at the California Institute of Technology, in papers in Physical Review Letters, and in his 2010 book, From Eternity to Here, is that if the universe arose as a thermal fluctuation from a high entropy background, then the smallest fluctuation sufficient to produce an observer is overwhelmingly more probable than a fluctuation that produces an entire ordered universe containing that observer. The minimum fluctuation required to produce a single self-aware structure, a brain, with the sensory impression of existing in an ordered universe, complete with false memories of a coherent past, is incomparably smaller than the fluctuation required to produce an actual ordered universe. Carroll formalized this as the Boltzmann brain problem, in an eternal universe governed by statistical mechanics. The vast majority of observers at any given moment are not beings who evolved in a structured cosmos, but disembodied cognitive structures that spontaneously fluctuated into existence from thermal noise, complete with the subjective impression of having done otherwise, and will dissolve back into noise within moments of their formation. The Boltzmann brain is not a metaphor. It is a precise statistical prediction of eternal inflation combined with thermodynamic equilibrium in the late universe. Andreas Albrecht at the University of California, Davis, and Lorenzo Sorbo at the University of Massachusetts Amherst published a paper in Physical Review D in 2004 calculating the rate at which Boltzmann brains would nucleate in a de Sitter universe, the exponentially expanding spacetime. Our universe is approaching as dark energy comes to dominate, and found that over sufficiently long timescales, the number of Boltzmann brains produced by quantum fluctuations in the expanding vacuum would exceed the number of ordinary observers who evolved through cosmological history by an arbitrarily large factor. Don Page at the University of Alberta has argued in multiple papers in Journal of Cosmology and Astroparticle Physics that any cosmological model that produces more Boltzmann brains than ordinary observers over its full history is thereby falsified, because the overwhelming majority of observers in such a model would be Boltzmann brains whose observations were unreliable. And reliable observation is the precondition of doing cosmology at all. What makes this genuinely creepy, rather than merely a technical problem for inflationary cosmology to solve, is the inversion it performs on the concept of the watcher. The prior items in this sequence have traced the possibility of something outside our dimensional frame, something on an adjacent brain, something reading our holographic boundary, something running our simulation, something whose observation collapses our quantum states. The Boltzmann framework introduces a different kind of watcher, one that arises inside the system, from the system's own thermodynamic noise, possessing full cognitive function and a complete subjective history, and dissolving back into the background within moments of its formation. The Boltzmann brain is not watching from outside, it is watching from inside, briefly, without origin, and it is statistically the most common kind of observer in an eternal universe. The mainstream cosmological response is that the Boltzmann brain problem is a genuine theoretical constraint on cosmological models rather than a description of reality, and that it motivates the search for cosmological histories that do not allow sufficient time or de Sitter volume for Boltzmann brain nucleation to dominate. Carroll has argued that the problem rules out the simple eternal de Sitter model of the universe's future and requires a cosmological scenario in which entropy production continues indefinitely rather than approaching equilibrium. Raphael Busso at the University of California, Berkeley has proposed geometric entropy bounds that may limit Boltzmann brain production in realistic cosmological models. The theoretical community takes the problem seriously as a constraint, not as evidence that Boltzmann brains actually exist in numbers that matter. What that response does not resolve is the prior question the framework generates before it becomes a cosmological constraint problem. The Boltzmann brain argument demonstrates that in any universe old enough and large enough, spontaneous observer structures with full inner experience and no causal history connecting them to the ordered universe they seem to perceive are not merely possible, but statistically mandatory, not rare, dominant. The ordered universe you appear to inhabit, with its coherent past and its structured physics and its sequence of items building carefully toward a conclusion, is, on pure statistical grounds, less likely to be the explanation for your current experience than the alternative that you are a thermal fluctuation reading a false memory of an ordered world, in a universe that is mostly noise. That alternative cannot be ruled out from inside the experience it would produce. The thermal fluctuation and the evolved observer feel identical from the inside, because the thermal fluctuation includes, by construction, the feeling of not being one. The prior items described something watching us from outside. This one describes the possibility that the watcher is us assembled from noise, temporarily coherent, reading a universe that may exist only in the fluctuation that produced the reading. Number 1. The threshold. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen, working at the Institute for Advanced Study in Princeton, New Jersey, published a paper in Physical Review, Volume 47, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" A paper that identified what they considered a fatal defect in quantum mechanics and inadvertently identified the most disturbing structural feature of the universe that physics has yet found. The paper demonstrated that quantum mechanics, as formulated, implied that two particles that had interacted could subsequently influence each other's measured states instantaneously across arbitrary distances, that a measurement performed on one particle would determine the state of its partner regardless of the separation between them, with no time for any signal to tween them at any speed. Einstein called this spookhafte Fernwirkung, spooky action at a distance. He intended it as a reductio ad absurdum, a demonstration that quantum mechanics was incomplete, that some deeper theory with local hidden variables must underlie it. In 1964, John Bell at CERN published a paper in the journal Physics, Volume 1, deriving a set of mathematical inequalities that any local hidden variable theory must satisfy, and that quantum mechanics predicted would be violated. Between 1972 and 2015, experiments by Stuart Friedman and John Clauser at the University of California, Berkeley, by Alain Aspect and collaborators at the Institut d'Optique in Paris, and by a loophole-free test conducted by Bas Henson and collaborators at Delft University of Technology, published in Nature in 2015, confirmed the violation of Bell's inequalities with statistical significance exceeding 12 standard deviations. The local hidden variable theory Einstein required does not exist. Aspect received the Nobel Prize in Physics in 2022 for his contribution to this experimental program. The universe is non-local. That is not a philosophical position. It is an experimental result. Place that result alongside everything this sequence has established. The Kaluza-Klein framework established that extra dimensions thread every point of three-dimensional space at a scale below our resolution, present everywhere, pointing in directions we cannot access. The brain collision hypothesis established that our universe may be a membrane that was struck into existence by an adjacent structure that remains separated from us by a gap we cannot cross, in a direction we cannot point to, possibly at a distance that is geometrically negligible while being physically absolute. The holographic bound established that the information content of our entire observable universe is encoded on a two-dimensional boundary surface facing outward, at a density of 1 bit per Planck area, readable in principle by anything positioned on the other side of that surface. The dark matter shadow established that 5 times as much of the universe's matter as we have ever detected inhabits a physical sector that interacts with ours only gravitationally, threading every room and every body and every cubic centimeter of space we have ever measured, invisible to every instrument we have ever built that operates through any force other than gravity. The simulation boundary established that the computational substrate running our physics, if it exists, is positioned at a scale of resolution below everything we have ever measured, producing no signature in any experiment conducted at accessible energies, and is structurally indistinguishable from the absence of any substrate at all. The quantum eraser established that observation determines physical outcomes across time, that what something was doing before it was measured is settled by a decision made after the measurement. The fine-tuning of constants established that the parameters of our universe appear not merely compatible with observers, but calibrated for them, positioned at the edge of the observer-compatible range, with a precision the landscape of possible universes does not, by itself, explain. The Boltzmann framework established that, in an eternal universe, the dominant class of observer is one that assembles from thermal noise without causal history, indistinguishable from inside from an observer with a genuine past. And the measurement problem established that quantum mechanics, the most precisely confirmed physical theory in the history of science, requires observation to produce definite outcomes, has never defined what observation is, has never identified what performs it, and has operated for a century on a postulate whose mechanism is formally empty. Every piece of evidence in this sequence is real. Every researcher is real. Every journal, every volume number, every Nobel Prize, every experimental result, is verifiable. The Institute for Advanced Study in Princeton, the Institut d'Optique in Paris, the Howard Hughes Medical Institute's Janelia Research Campus, CERN, the Planck Satellite, the Pierre Auger Observatory, the Delft University Loophole-Free Bell Test, the 20,000 citation Maldacena paper, the Born rule confirmed to 1 part in 1 trillion. These are not invoked for atmosphere. They are the evidentiary foundation of a set of findings that, taken together, describe a single structural situation from 10 different directions simultaneously. The situation is this: the universe, as currently understood by the best confirmed physical theories available, has an inside and an outside. The inside is where we are three-dimensional, bounded by a holographic surface, threaded by undetectable matter, governed by quantum mechanics that requires an observer, finely tuned for the existence of observers, and non-locally connected across all distances instantaneously by entanglement that no local mechanism explains. The outside is wherever the extra dimensions go, wherever the adjacent brane is, whatever reads the holographic boundary, whatever runs the substrate, whatever the dark sector's parallel physics describes, whatever performs the observation that quantum mechanics requires and cannot define. The inside and the outside are not separated by distance. They are separated by the structure of the physics. The outside is not far away. It is adjacent in a direction that the inside cannot access, at a resolution the inside cannot reach, on a surface the inside faces but cannot turn around to see. The question this sequence was announced as investigating was whether something is watching us from another dimension. That framing assumed the watching was the strange part, that the existence of an observer outside our dimensional frame was the hypothesis requiring defense. What the sequence has established is that the watching is not the hypothesis. It is, in the most precise available sense, the default. Quantum mechanics does not work without it. The wave function does not collapse without it. The Born rule does not produce outcomes without it. The theory that describes every particle in the observable universe at its most fundamental accessible level has, built into its operational core, a requirement for observation that it cannot fill from inside the system it describes. The observer the theory requires is, by the theory's own structure, not fully contained within the universe the theory describes. This is not a fringe position. It is the unresolved center of the most successful scientific theory ever constructed, documented in the foundational papers of Born, Bohr, Heisenberg, von Neumann, Everett, Bell, Aspect, and Zurek, debated without resolution across 100 years of physics, and present in every quantum mechanics textbook currently in use at every university on Earth. You have been watching this sequence from inside a universe that the sequence's own physics requires to be watched. The 10 items did not describe 10 separate anomalies. They described 10 independent lines of evidence converging on a boundary, the boundary between the inside of the universe and whatever is adjacent to it, whatever reads it, whatever the observation postulate requires to be there. The creepiest theory about something watching us from another dimension is not a theory. It is the operating assumption of the physics, stated plainly. With the comfortable interpretation removed, the equations require a watcher. The equations cannot tell you what it is. They can only tell you, with 1 part in 1 trillion precision, that without it, nothing in the universe would ever happen at all. If you want to see more videos like this, click the video on screen now, and make sure to subscribe.